In this video, I will discuss how we can solve coupled first order differential equations, and then that will naturally lead us to a method for handling higher order differential equation using numerical methods. We need coupled equations solution method because many times in physics we get a problem where there are more than one variables that are changing with respect to an independent variable. For example, in a projectile motion, the coordinates of the particle, let's say if the particle is in a plane, the x and y coordinates are changing with respect to time, and we have two differential equations, one for x and one for y, where there are multiple forces, for example, force of gravity, drag force, and so on. So we will begin by discussing how to solve coupled equations, and I'll just take a two-dimensional case because that's the common one and also easier to illustrate. You can easily extrapolate it to more than 2 dimensions if you want. And then I will discuss higher order differential equation, and specifically second order differential equation because they are the one which are most commonly present in physical problems. Okay, suppose that I have two first order equations and I can solve them to get an equation like this and another equation like this. And so in this equation there is only one dy by dt, and here there is only dx by dt on one side, and everything else, there are no derivatives on the right side, but the function can have both x, y, and t. And if you get a system of equation where you have, let's say, dv by dt and maybe dx by dt also in this equation, and also in the other equation you have dy by dt and dx by dt, etc. So first, before beginning this method, what you should do, you should simultaneously solve them, because there are two like these variables and two equations. You can solve them to get one equation with dy by dt only and the other equation with dx by dt only, and everything else on the other side. Okay, so we'll assume that that has been done, and we have these two equations, and there are two initial conditions, because now we have two variables. So there are two initial conditions. Let's say we are given value of y at initial t, which is y naught, and then we are given initial value of this variable x naught. We already know how to handle first order single differential equation using Euler method and backward Euler method. So I will use those methods to illustrate how we can solve these equations. So let's begin the solution using simple Euler method or forward Euler method. So we can use that method to quickly write the iteration equation for this, which is yn plus 1 is yn plus h f xn yn tn. So and similarly for this, I have xn plus 1 xn plus h gxn yn and tn. I have already explained in a previous video how do we solve a first order differential equation using Euler method and get this equation. Now for this coupled system, the point is that when you begin solving, you cannot solve this equation independent of this equation. You have to solve both equations simultaneously. So in the first iteration, at n is equal to 1, you have values t0, y0, x0, because they are given here in the initial condition. We have y0, x0. We can select this interval h. We plug them here and we compute y1 and x1 right now. And then we use this x1, y1 in the next iteration, t1, y1, x1, t1, y1, x1, and compute y2, x2 in one step, and then y3, x3, and so on. What we cannot do is just keep on computing this and forget about this. That will not happen, because at each step we not only need new y, but we also need new x to find the next value of y. So this is the major difference of setting up a coupled system of equation, that we have to solve them together at each step. If you want to, use the backward Euler method, for this coupled system, what we can do is that we can use this forward Euler method to get what we call guess values. And once we have these guess values at each step, we can find the so-called correct value as yn plus fxn plus 1, which is now guess, yn plus 1, which is now the guess value, tn plus 1, and the so-called corrected xn plus 1 as xn plus hg xn plus 1 guess, yn plus 1 guess, and tn plus 1. So in backward Euler method, at each step we actually compute 4 equations. First these two to compute these guess values, and then right in the same iteration we use these guess values to compute the corrected y and x values, and then we go to the next iteration. So this is how we can solve coupled first order differential equations by solving these equations together. Okay, let's now see how we can use this thing to solve a higher dimensional equation. So the method is simple. What we do is we convert the higher order differential equation into a system of first order differential equation, and then solve them just using the methods that I have described. That's the only point that we have to remember. So as an example, let me start with a second order differential equation. Suppose I have this equation to solve. There is some coefficient, let's say, of y and t, and then dy by t, and this is equal to some function of y and t. So we have one dependent variable y and one independent variable t. So this is a general second order differential equation. It doesn't matter if the coefficients are constant or not, and also we can have a forcing function, no problem with that. We can solve an arbitrary second order differential equation using this numerical method. So what we do, we can convert this second order equation into a system of first order equation by using substitutions. Before I do that, let me also point out that with this equation there are two initial conditions, and they are that the function, let's say, is given at some time t naught, we call it y naught, and then the derivative of this function is also specified at this variable t naught. Let me call it some, z naught, whatever that number is. Let's call it z naught. Okay, now let me convert this equation into two first order equations. And for that, let me make this substitution. Let's say we define this dy by dt as some variable z. So if I do that, let me substitute here. So this d square y by dt square, this will become d z by dt, and let me take this side to the other side. So on the right side I have this b of yt, and this becomes minus a of yt, and this dy by dt is now nothing but z. So now I have these two first order equations. There are two unknown now, y and z. This t is independent variable, and on the right side we have some function. So earlier we discussed that if this is, let's say, some dy by dt and then some function f, so that general function is now very simple, only z, the variable which is being used here. And I can transform these initial conditions very easily to here. So these set of initial conditions, this now transforms like this, that this is same, and the second condition is z of t naught is now z naught. So I have set up this system. There are two initial conditions for both of these unknowns, and there are two equations, and we can use Euler or backward Euler method, or eventually any other method as well, to solve these equations simultaneously. And at the end, what we will have is this. We will have z naught, z1, z2 up to cn, and we will have y naught, y1, y2, and up to yn, where I'm assuming that we divided our interval into n+1 points. Now, since our interest in this case at the end is only in the solution y, it's up to you if you want to keep track of these z's throughout by saving them in some list or some array or not, or you can keep them saving and at the end just don't use them. But if you are interested in the derivative of this function, you can keep them, because this is nothing but the derivative of this function over here. But most importantly, we have been able to find our solution of the second order differential equation. Thank you.